This conference will now be recorded.
So, very good morning, students. Today, we will be learning first law of thermodynamics in detail. We had already started with this topic, but we had not discussed in detail. So, I'll recap a little bit and I'll discuss in detail about first law of thermodynamics. Then we'll learn a very important topic, molar specific heat of gas. So, this thing we had already discussed in the thermal property of matter, but again here we'll learn this in different way. Further, this will be again discussed during kinetic theory of gas. There also will be learning few new aspects of specific heat of gas. Okay, and the important thing is the PV graphs in thermodynamics. So this graphs indicates many good thing about the state of a particular thermodynamics. So how do we know about that? From the graphs we will see. And finally we'll see work done in cyclic process, etc. So let us enjoy the class. Okay, so we'll start now. As we discussed in the last class, the first law of thermodynamics, simply the law of conservation of energy. What is done in this thermodynamics? Sorry, first law of thermodynamics. Here actually we'll discuss that some type of energy, some kind of energy, whether it is in the form of work or heat, will be supplied to some system, and that if suppose we give heat, that will be transferred into heat or work or both, and that can be done to the system or done by the system. Okay, so there is an interaction between surrounding and the system. Okay, so here the law of conservation of energy involved both with both with the system and the surroundings. So it is simply the law of conservation of energy, where energy is supplied. Here there is missing. So energy is applied to a system, to any system, gets transferred from or to the surroundings in the form of heat or work done. So this is briefly about what is thermodynamics, first law of thermodynamics. Now we'll learn in detail. So what is the statement of the law? The statement of the law is that if some heat is supplied to a system which is capable of doing certain work, then amount of heat absorbed by the system will be equal to the sum of the increase in its internal energy and external work done by the system on the surroundings. So you can see this mathematics we had already, this mathematical formula already we had written in the last class. So dq, suppose dq is the heat energy which is supplied or applied to the system, and internal energy, we know internal energy is for ideal gas, it is directly proportional to temperature, that we know. And work done, it is it can be written as p and delta v, that means change in the volume into pressure, work done. So work done by the system on the surrounding, and this is du is change in internal energy. So if these are according to the first law of thermodynamics, we can write dq, the total heat which is absorbed by the system, will be equal to the change in the internal energy, that is del U, plus this is delta W. Okay, so delta Q is equal to delta U plus delta W. Delta W is the work done by the system. Okay, work done by the system. So this is the, so I'll write today once again. So this is dq. This is the mathematical form of, this is basic mathematical form of first law of thermodynamics. Okay, this is mathematical form or analytical form, you can say. First law of thermodynamics. Okay, so now we'll elaborate on this. See, experimentally we'll see how we can verify this first law of thermodynamics. That means del q, this equation del u plus del w. Okay, this is not, please remember this, this is w means work done. Okay, so in this figure we can see this is a gaseous system, and the gas is actually inserted in a cylindrical container, and that container is with a movable piston. This is actually a movable piston. Movable piston. This is piston. See the system, gas is inserted in a cylindrical container which is fitted with a movable piston and generally taken as massless piston and smooth, so that no energy loss is happening in this during this movement of the piston. Now there is a constant pressure. Constant pressure is applied on this gas. Okay, some pressure is there on the gas because this piston is there. Now this is the amount of heat. It is, see, this is the surroundings. Okay, this is the surroundings. From the surroundings, the gas is absorbing some amount of heat, that is delta Q. Okay, delta Q heat is absorbed. So this is the heat absorbed by the system. This is heat absorbed. This amount of heat is absorbed by the gas. After absorbing the gas, heat energy, what will happen to the gas? Actually, there are two possibilities. One is that temperature will rise. Okay, so if temperature rises, then what will rise? Internal energy rises. So this is another option is that, see, because the gas, if the kinetic energy increases, so they will exert pressure on this piston. Suppose this is the initial position of the piston. Now you are heated, like the gas is heated, and you can notice that the piston will be moving up slowly because the gas molecules, they will gain extra kinetic energy. With that, they will actually heat the piston. So there will be a thrust on this, upthrust on this piston, which will move the piston up to here against this external pressure. That means the gas is working on the system. Sorry, the gas means system. It is working on the surroundings. Okay, so there is a possibility of work done by the gas, because gas will be expanding, and due to expansion there will be work done against the external pressure, work done by the gas. Okay, against external pressure. So these two things happen. So look here, from here we can find out what is this work done. Suppose the gas was here initially, sorry, this piston was here initially, and piston has area of cross section A, okay, area of cross section A, and it was given a constant pressure that is P. You can see that. Now when the gas is heated or gas absorbs this delta Q amount of heat, it will expand and it will work against the external pressure. And suppose because of that the gas, because of the expansion of the gas, there is a displacement of this piston by sorry, dx. So this is the displacement of the piston of the piston displacement of the piston, okay. So then calculate work done by the gas. We know work done means force into displacement, force into this. So what is the displacement over here? Oh, that is dx, okay. Or we written delta here, this we should have written delta x, okay. Let it be delta x. What is the force here? See, this gas is working against the constant pressure, this P. That means force will be P into area of cross section of the piston, that is A. This is the force. We know thrust into, sorry, thrust by area will be pressure. So pressure sorry, thrust will be pressure into area. That means this is the force and displacement is delta x. So from here we can find, so this is F delta x or dx, whatever you can write. So actually nothing but see, P F is actually P into A, I said. So P A into dx, A into dx is dv. So P delta right delta. So this is P delta V. Hope you agree with me. So the gas is expanding its volume due to the heat absorbed from the surroundings. Okay. So because of that, it is actually doing certain work. So that can be calculated force into displacement. Force is thrust in pressure into area. So P is pressure against which the gas is working. So P into A, area of the piston. So PA, this gives the force. This delta x, this is the displacement of the from here to here. So A into dx, see that this is the volume of this, okay, volume of this. So A dx, the change in the volume. So A dx is the change in the volume, so we can write P dv. So here P dv means, dv means A, area of cross section, into change in the or displacement of the piston. So this is actually volume. Actually this shaded region is dv, okay. You have to see that. All right, so this is about first law of thermodynamics. Now if suppose, okay, so this is work done already, we know. So see, this form will take another form, that is du plus p delta v, or this can be written in terms of d. So dq, sometime it is written like this, dq. So cross over here, I'll tell you why. So du plus p dv, this you can see in your some other textbooks, you can see this. So why this is cross? Because this is not a state function, this is state function, it depends on path. That's why sometimes it does, actually it should not have a total derivative. That's why this bar is the, okay. So dq is equal to du plus pdv, where du, see, PdV also is not a state function. This is also not a state function. This is not a state function. Only du is the state function. We had already discussed. Du is only the state function. Okay, so we will clean everything and we'll write what we have got. So dq is equal to change in the internal plus work done p delta v. Okay, this now you be given this and this, you have to find out what is the volume change. You might be given this whole term, you might be given this, what is the energy, you have to find out sometime internal energy, and this will be given what is the pressure. This kind of questions will be in exams. Okay, so we'll go to the, okay, see here, if the gas expansion is happening, that is fine. If the pressure is increasing or decreasing, volume remains the same, so this term will be 0 then. Okay, so now we'll go to the next topic, that is specific heat. We'll first discuss what is specific heat. This we had already discussed in the properties of matter part, but still we'll recap a little bit and then we'll go ahead. So when a gas is heated, its volume and pressure change with increase in temperature. Volume and pressure both will change in increasing temperature. So the amount of heat required to raise the temperature 1 gram of gas through 1 degree centigrade is that is gas, like that is a gas does not possesses unique or single specific heat. So what I'm going to mean here, when a gas is heated, its volume and pressure changes. So like we all agree. So the amount of heat required, temperature of 1 gram through 1 degree centigrade is fixed. For every element, they have their own heat. That is a good. Sorry, that is gas does not possesses unique or single specific heat. Now, specific heat depends on the condition under which it is heated. See, amount of heat will be depending on the condition, like at what condition a gas is heated, whether the gas is heated at constant pressure, constant volume. So these things matter a lot for when it is concerned with the amount of heat. Okay, so we'll see there are main two types of specific heat. Two main types of specific heat. Since we have already discussed these things, I'm not writing too much for this, but whatever new here we'll discuss. Let me write in terms of mathematical formula. Uh, okay, so specific heat Okay, so there are actually two types of specific heat. Before that, we'll write in terms of mathematics. Okay, so let me go to the specific divisions itself. So there are two types of two types of specific heat of a gas. Specific heat. Heat of a gas. As I was discussing, the specific heat depends on the condition in which the gas was heated. So specific heat of a gas can be of two types depending on at what condition they are heated. One is the specific heat at constant specific heat at constant volume. What does that mean? And how do you denote it? Those things we'll discuss. So when a gas is heated at constant volume, then it is called specific heat at constant volume, and it is denoted by CV. And then other one is specific heat at constant pressure. So that is CP. That is written as, like, that is denoted by CP, and specific heat at constant pressure. So if we define the molar specific heat at constant pressure and constant volume, how do we write? And what happens with this? We have to see. So we'll write molar specific heat at constant pressure. Molar specific heat at constant volume. Let me write first. Is. So it is the amount of it. It is as defined as the amount of it required to raise required to raise the temperature of a 1 mole a gas through 1 degree centigrade at constant volume. Molar specific heat at constant volume is defined as the amount of heat to raise the temperature of a 1 mole of a gas through 1 degree centigrade at constant volume, and it is denoted CV. Look, in this case, if I write of first law of thermodynamics, see when we apply amount of heat to a system at volume, what happens? We know du plus dv. This we know. Okay, let me write delta itself. So delta v. So at constant volume means what? Constant volume means this dv is 0. So what this implies is dq, the amount of heat which is required the temperature of a gas through 1 degree centigrade is doing only one work. What is that? Only one way the amount of heat, this dq, is spent is the internal energy, because to raise the temperature itself. So this is the case. Excuse me. So at constant volume, when we supply some amount of heat to one mole of gas to raise the temperature by 1 degree through 1 degree centigrade, then that amount of heat is actually called molar specific heat. Okay, so here this the definition, actually the definition of specific heat is actually the amount of heat per degree centigrade, like that. So dq by dt. So from here, if you want to calculate cv, cv can be written dq by dt. Okay, delta t at constant volume, at constant volume. That means this will be, so this is actually at constant volume when volume is constant. So this will be del u by del t. Okay, I hope you have understood the definitions. I'll write the mathematical part. So first law says dq will be equal to du plus p del v. Sorry, let me write terms of derivative. dq is equal to d plus p dv. Okay, so when v is constant, then this p dv, this term will be 0. Q will be du. And according to the definition of specific heat, C is equal to dq dt. Okay, the amount of heat required to change the temperature by unit degree centigrade. So this dq by dt. Okay, at constant volume. So this I can write as CV. Excuse me. So this is dq by dt at volume v. So we can write du dt at constant. Okay, this is specific heat at constant volume. So the amount of heat you supply to the system spent that particular amount of heat energy is spent in increasing the internal energy itself. So this is CV. So sometime, sometime we can write is equal to CV dt from here. We can sometime see dq from here. We can write CV into dt. See from here. We can from here CV dt. We can write sometime du dt, or we can write CV t. Okay. So this is also another formula to remember. dq is equal to cv into dt. Okay, now we'll see. Let me write here. So cv is equal to dq by dt at constant volume is du by dt at constant volume, but it does not see u does not depend on v. Internal energy does not depend on v, only on temperature for ideal gas. Okay, now we'll in this part we'll define what is Cp, or specific heat, molar specific heat at constant pressure. So this is going to be very interesting. So molar heat at constant pressure is defined as, it is defined as the amount of heat, amount of required to raise the temperature of 1 mole gas, to raise the temperature of a 1 mole gas through 1 degree centigrade at constant pressure. At constant pressure. Okay, this is called Cp. This is denoted by Cp. Okay, so this is denoted by Cp. Let me tell you one thing. Here again, if we apply the first law of thermodynamics mathematical formula, so dq is plus pdv. Constant pressure means this term will be there, obviously. Let us do the derivative part. So dq dt. So in this case, like, see, when we apply certain amount of heat to a system and raise the temperature at constant, then what happens? The amount of heat we supply to the system will be two ways. One is to increase the internal energy, and this is the one by the gas on the surroundings. Gas work done by the gas on the system. Oh, sorry, anyway. So here you have something. The amount of heat absorbed by the system is actually doing two things. One is this du. Earlier also it was C. Du was already intact, and additional is here PdV. That's why Cp can be Cp can be written as Cp can be written as du dt at constant pressure plus dv dt at constant pressure. Okay, since this du does not depend on pressure, we can just neglect this in index. But this term is extra. You can see Cp, we know Cp is Cv is equal to dq is equal to Cv into dt, but in this case you cannot write Cv into dt. So there is another term over here. So look, this, if we write Cv u dt, Cp minus Cv, this part you can see that this is the term. In case of yes, here. You can see there is an extra term over here at constant pressure. When I write constant pressure, so Cp can be written as dqdt at constant volume, and there will be, this is all right, dqdt at constant. So this will be dqdt at constant pressure plus p dv at constant pressure. So this term, this index we can remove because internal energy does not depend on volume and pressure both. So it, among these two specific heats, see both the right hand side. See, the first term is same. In both cases, amount of heat we supply is spent to increase the internal energy. Some part, in case of this, actually the whole part doing the same job. But in case of CP, part of the heat energy is used to do work against the pressure P. Okay, so then you can see from here itself that P is greater than Cp because Cp has this additional term work. Okay, so work done turn. So Cp is greater than Cv. So how much greater than it is? Cp minus Cv you have to do. Then you will see Cp minus Cv will be Cv P into dV dt at constant pressure. Okay, so this is the difference in the two specific heats, and these two specific heats are called the principal molar specific heat of gas, principal molar specific heat of a gas. Okay, Cp and Cv, and the difference is, sorry, we'll then remove this part. So we can see Cp minus Cv is equal to P dV dt at constant pressure. So this is what is the extra term over here. Now look, for an ideal gas, we know PV is equal to RT for 1 mole gas, at least now for 1 mole gas. So we can write P dV dt is equal to R dt by dt. Okay, this is also dt. So what does this imply? P dV dt is equal to, that means this P dV dt is equal to R. So Cp minus Cv is what? Cp minus Cv is R. This is always true. Cp minus Cv will be R. So the energy required, a relation between Cp and Cv. So this amount of energy, this is the extra energy R. This is the extra amount of energy that is required. So Cp minus Cv is equal to R. This is actually universal relation. Okay, Cp minus Cv is equal to R. Okay, I'll write again. Cp minus Cv is equal to R. So this is actually in terms of units of according in the unit of heat. So this is in the unit of heat. Cp minus Cv is equal to R. Cp minus Cv is equal to R by J. This is in terms of, sorry, in the, let me check one thing. Okay, the first one was actually in terms of work, not in terms of heat. In the unit of work. Cp minus Cv is equal to R by G in terms of heat. Heat energy. So this is the relation between Cp and G, and see the excess energy, the difference between the specific is equal to the amount of heat equivalent to work done performed by gas during expansion at constant pressure. I'll just write this statement. You can just meditate on this statement. The difference between the two specific heat. The difference between specific heat. The difference between the, oh, this is two. The two specific heat equal to the amount of equals to the amount of heat required. Okay, so amount of heat equivalent to equivalent to work done. Work done performed by the gas. Performed by, so work done performed by the gas during expansion of expansion during expansion at constant pressure. Sorry, this will be constant pressure. Okay, expansion at constant pressure. Okay, so this you have to remember, this R is actually in terms of unit of R, in terms of unit of work done, and R by J in terms of heat. Okay, so this is about molar specific heat, and one short thing I'll just tell you here, that Cp by Cv, molar specific heat at constant pressure, divided by, sorry, to the Cv. So Cp and Cv, the ratio of Cp and Cv at constant pressure by constant volume. So this will give you a constant. This is called gamma. So this is called gamma. This depends on atomicity. Atomicity means how many atoms are there in a particular molecule. That is atomicity. So we'll see that in kinetic theory of gas how Cp by Cv, that is gamma can be calculated. How gamma can be calculated. So that we'll learn later in the kinetic theory of gas. Okay, so we'll go to the next topic, that is PV diagrams and work done during cyclic process. PV diagrams or indicator diagrams. So with this we'll stop today's class after discussing the PV diagram or the indicator diagram. Work done by cyclic process will be discussed in next class. So we'll now discuss only this PV diagram or indicator diagram. So what is this PV diagram or indicator diagram? See, in mechanics we have seen many things we had expressed like velocity, then acceleration, displacement. These are the things we had discussed graphically also. So when we talk about thermodynamics, the state of thermodynamic system can be completely described by two thermodynamical variables, namely pressure and volume. Then actually there are three. There are three main state variables. Those are pressure, so pressure and then volume and temperature. These are the main three variables which actually determines the state of a system. Obviously internal energy, other things are there, but these are the main things. These are macroscopic parameters also. So by simple experiment you can find out these things. So to specify a thermodynamic system completely, we need at least two parameters out of these three. PVT. Why? No, uh, if we know only two parameters, other parameter anyway fixed, that will not vary with these two according to it. Okay, so a graphical representation of the state of a system with the help of two thermodynamical variable is called the indicator diagram, okay, or PV diagrams. Here P and where is there, the two parameters are P and V, that they are called PV. When there are PT, then pressure temperature diagram, and V versus T, that is uh, volume versus temperature graph. Okay, so what is an indicator diagram? A graphical representation. This is actually a graphical representation a graphical representation a graphical representation of the state of a system, of the state system with the with the help of two thermodynamical parameters. Help with the help of two thermodynamical variable. Variable is called an indicator diagram. Okay, so this is called indicator diagram. So generally we take PV, and there is a beauty of PV diagram as well. We'll see today. We'll just start with that, and later on. Okay, suppose a system is undergoing. See, this is volume, and this side it is pressure. Okay, along x-axis is volume. So when a gas goes from a state, suppose A to some position B in this way, okay, so it goes like this, suppose. Okay, so this is B point. When it goes, sorry, B to A, suppose here the pressure was P1. Okay, at this particular position pressure was P1 and volume is V1. And see, at this position this volume has got a value V2, and it has some other value of pressure, that is P2. So pressure is here, then P2, and the volume is V2. So in this case we can see that V2 is greater than V1 in this. See, this is V1, sorry, V2, this is V1. So therefore we can say, what we can say, this the gas is undergoing an expansion. Okay, an expansion isothermal, you can say. We have kept the temperature constant, so this is an expansion. So this is a process of expansion of the gas. If we go from A to B like this, if we just change the arrow, then it is called compression. It is called compression. Okay, suppose this is, so when we say that V1 is, anyway, V1 is smaller, so if the arrow is like this, then it is compression. This is compression. Okay, so this is actually PV diagram or indicator diagram. See, what is the beauty of PV diagram? PV diagram, area of PV diagram, area of a PV diagram area of a PV diagram gives the heat energy sorry, not heat energy, the amount of work done, sorry, not the heat energy. Area under the PV diagram gives the work done by the gas or on the gas, by the gas or on the gas. Okay, so PV diagram, the area under PV diagram will give you the work done by the gas on the system, sorry, on the surroundings, or the work done on the gas by the surroundings. Okay, so I will stop it here for today. We'll discuss this PV diagram and work done in cyclic process, during cyclic process, and uh, other things related to this PV diagram, PT diagram, VT diagram, etc. So those diagrams we will first finish along with various processes, then we'll move further. Okay, all right. So this is all for today. We'll meet again tomorrow with the same chapter, thermodynamics. Okay, so bye for today.